Hey guys, so this is us getting going into 4.6. 4.6 is one of the most pivotal moments in Algebra 2, where we really take a step from traditional basic algebra that makes total sense, or at least should make total sense in the world that we live in. And we're going to take a step into the unknown a little bit. We're going to take a step in a direction that we've never really dealt with before. And to this point, your teachers have probably done a pretty good job of convincing you that what we're about to do is actually impossible. But what you need to understand is that we're going to start to give some real depth to the number system. When we think of numbers, we count. Sometimes we divide the numbers that we're counting into smaller portions, and we have this idea of decimals and fractions. But at the end of the day, I can still take, an M&M, and I can split it and cut it, and I can come up with most of the numbers that you've ever thought of. I can make a portion of this M&M into that number, or I could multiply it by 1,000,000 and have 1,000,000 M&Ms. But to be able to do what we're going to do today is beyond what we would traditionally consider normal or even real. It has to do with taking the square root of a number. The square root of 9 is positive or negative 3. We have to pick one, but if we were to pick one, say 3, it's 9 because 3 times 3 equals 9, or negative 3 times negative 3 equals 9. We can prove that this does work. It's multiplying a number by itself to produce the result. If, however, I try to take the square root of negative 9, we run into this problem. Because if I use a positive 3, I'm supposed to use a positive and another positive 3. If I use a negative 3, I'm supposed to use a negative 3 times a negative 3. But somehow I have to get a negative. And we've learned for a long time that a positive number times a negative number is the only way to produce negative results. So for the longest time, when you were first introduced to square roots and the idea of a square root, you were told that this was not possible. And that is true and false at the same time. It's true if you use what we're going to call real numbers. Now, when we talk about real numbers, what we mean is the physical numbers that we can add, subtract, that we make real simple sense of. They're numbers that show up on the number line, either the x-axis or the y-axis. We can plot these points as real things that it totally makes sense to us. However, there are problems where the solution to that problem isn't one of these numbers. It isn't one of these traditional real numbers. And so we introduce what are called imaginary numbers. Now, it sounds made up. And the truth is, at some point, I think that was initially thought, like, hey, this is just a filler. We just said, well, how do we solve these problems? Let's make something up. But over time, as we've come to understand mathematics and how it models the real world, we've actually found that imaginary numbers play a critical role in modeling things like electricity, modeling how air current flows around different objects. Imaginary numbers have found their way into the everyday society that we live in. We need and depend on these numbers just as much as we need and depend on our what we call real numbers. So let's start by giving a definition of what we mean by an imaginary number. To make this as simple as we could, we just took the square root of negative 1. So now that is something that we know doesn't have a regular answer. And it can be, the square root of negative 9 can be written as the square root of positive 9 times the square root of negative 1. So all of these square roots of negatives can be turned into a real root times the square root of negative 1. So we decided to define the square root of negative 1 as the value. Because it comes from this concept of imaginary numbers, we use the lowercase or script I. You can use a cursive I if you want, something like that, to represent the square root of negative 1. What this means initially, is that if I have the square root of negative 9, it can be written as the square root of 9 times the square root of negative 1. We learned about that last time. We know the square root of 9 is really 3, and the square root of negative 1, instead of writing root negative 1, we can replace it with its variable definition and write this as 3i. It makes the writing a lot more compact, and initially that was kind of the goal. It's just, hey, I want to make it simple to write and talk about. But then some understanding came about of what exactly is this square root of negative 1, and what are some of its properties. For instance, this is really important. You got to know that. But what happens when we square I? We know that a square is supposed to cancel out a square root. So if a square cancels a square root, then I squared, by definition, is negative 1. This is our second definition that we need to have today. So let's make sure we understand what's really happening here. We just created an imaginary number, something that doesn't exist in our number system that we traditionally use. And yet, somehow it has a direct link to numbers that are real. Negative 1 is a real thing. You owe me $1. That's something we measure all the time. It's on the number line. And yet somehow it's being created or being linked to the imaginary numbers. That's a pretty crazy connection. And this is where we start to find out that if we've ever thought of math as like a thin layer of soil on the top, it's all the grass that you see, the plants that you see, but we never really dug deeper, never got down into what are the numbers really made of. Now we're getting down into the much more complex and much more rich environment that you get into as you dig down into the earth. This creates what we call the complex number system. When we talk about complex numbers, we're talking about any number that can be written as a real number or an imaginary number or a combination of both. So we have real and we have imaginary. A real number can't be combined directly with an imaginary number, but they do have interactions with each other. So for instance, if I take a complex number like 3 plus 2i and a complex number like 5 minus, let's go 4i, I can combine my real components and my imaginary components just the same as normal like terms. 3 and 5 makes 8. 2i and a negative 4i makes a negative 2i. So I can combine these complex numbers by addition and subtraction, multiplication, even division on some level can be done with these complex numbers. These complex numbers turn out to be solutions to some of the problems that we can't solve using the quadratic formula. So, for instance, we used to say that we were always looking for where these two values cross the x-axis. That was something we were really focused on. Well, the truth is, sometimes we get a graph that never crosses the x-axis. And yet the equation might still be able to equal 0 if we broaden our horizon. And as we broaden our horizon, we find out that problems like this have solutions, but they involve or include imaginary numbers. Now, in the homework, I'm going to go through a lot of the ins and outs over how exactly do we manage this idea of imaginary numbers and complex numbers. What are the calculations we would do? How do they really interact? And what's their purpose? So look forward to that video. Jump in and watch it as you're going through your homework to make sure you have the help you need. This idea of imaginary numbers is going to broaden and make possible finding solutions for things that otherwise seem imaginary and seem impossible to find. All right, good luck, and we'll see you in class.